All right, pre-algebra folks, since we are talking about inequalities in Unit 6, this interesting thing can happen where we have multiple constraints on an inequality or multiple inequalities, and they are called compound statements or compound inequalities. A compound inequality, if you want to just highlight, is a sentence with two inequality symbols or more. We're not going to get to more, but two inequality statements joined by either the word or the word by the word and those will have different meanings depending on the context. And we're just going to get a couple of real life examples of where you hear about compound inequalities and how they apply, and then how we could graph those on the number line. So the or statement means that the solution will be found either by satisfying constraint A or constraint B. Okay, so the solution can be in either pool A or pool B to make it true. An and statement means that the variable must satisfy both of the constraints, both of the inequalities. And that might sound really weird at first, but it'll probably make a little more sense when we apply it to just a simple statement like this. To audition for American Idol, a contestant must be at least 15 but under the age of 30. So let's think about what that means. A contestant must be at least 15 but under the age of 30. So when American Idol is trying out their contestants, they want people who are going to be the pop superstars. So you could have the just barely teenagers age, which typically make good pop stars, but no one, up into your 20s, you're still cool. But then if you get old like Mr. Cummings and over the age of 30, then you're not deemed like cool pop star anymore and they don't want you. Right? So auditioning for American Idol, a contestant must be at least 15 but under the age of 30. So let's see. Think about some numbers of values of ages that could satisfy the two constraints of the inequality. So if I make this algebraic, it looks something like this. N must be at least 15, greater than or equal to 15, but under the age of 30. And even though I'm using the word but under, you should probably say and. So to qualify to try out for American Idol, you must be older than 15 and under 30. So graphing this, what does it look like on the number line? Could I be 15, have turned 15? Yes, I could. So I'm going to use a closed dot, and I'm going to just draw an arrow going over 15. But I could not have turned 30 yet. A contestant is not able to have turned 30 yet. So in this case, I'm going to leave 30 open as a maximum limit. Oh, what the heck happened there? Leave 30 open as a maximum limit. Maybe I should grab this dot. This open dot. We'll leave 30 open and have an arrow going down here. And the solution space that satisfies both constraints are the ages in which you could try out for American Idol. So in this case, if you want to just highlight in the middle of 15 up to 29 and 300 days old or something like that, 29 point something years of age, right? That would be the compound inequality. So unlike yesterday where we just said n is greater than or equal to 15 and we graphed onto infinity, this one has an upper limit and under 30, right? What about this one? Citizens younger than 5 or over the age of 65 should take caution during the flu season. Citizens younger than 5 or over the age of 65 should take caution during the flu season. And I think everyone should take caution during the flu season, but these particular demographics are particularly vulnerable, I guess you could say. So younger than 5, how do we graph that? So younger than 5, let's say the variable is x. X must be, where's my pen? X must be younger than 5, under than 5, or x should be over the age greater than 65. Let's see what this looks like. So in this case, I'm going to go open dot on 5 again. Should look something like that. Open dot on 5. An arrow going down to the left because that is all of the ages that are younger than 5. Or x is greater than 65. So we'll go open dot on 65 over 65, over 65, and arrow going to the right, an arrow going to the right. Okay, so what does this look like? Instead of, let's consider the last graph. The last graph, we had a nice clean window of where n should be found. N should be, to try out for American Idol, you have to be 15, between the ages of 15 and 29.9, however you measure 0.9 of a year. But in this case, I find a little window of where x will not be found when you have an or statement. So you have arrows going in the opposite direction, either you're younger than 5 or you're older than 65. We have this blank space where x would not be found, right? To be in the pre-K 2 classroom, you must have had your second birthday and not yet turned 4. Must have had your second birthday. That means that you are at least 2 years old. So in this case, we'll use the variable y. Y's value is greater than or equal to 2, and y's value is not yet turned 4, is less than 4. So it has to satisfy both constraints. This is another and statement on this particular example. Y is greater than or equal to 2. Okay, so let's actually, could you have been 2? Yes, you could. So in this case, I'm going to graph with a closed dot on 2. And the arrow, which I'm not going to use that big arrow, I'm going to use a smaller one. The arrow, draw today, the arrow is going to be going greater than 2, yet and y is less than 4. Y is less than 4. So less than 4. Could I have turned 4? It says no, definitively not. You cannot yet have turned 4. So I'm going to leave 4 open with the open dot. And I'm going to point down from 4, as it says to do. Point down for 4. And then what we're going to do is we're going to shade the space that satisfies both requirements. So shade in between two, shade, don't move the thing. Come on, highlighter, you can do it. It's finicky today. We're going to shade that space in between 2 and 4. Go ahead, you can do it on your own paper. We'll just go ahead and drag it up like that. Perfect. All right, so anywhere between 2.0 and 3.99 are the ages that you could be to be in the pre-K 2 classroom, right? So if you want to write that, that kind of gives you a little more insight. Y's value, y. Well, I'm not allowed to write y's value. Must be equal to 2.0 all the way up to 3.9, repeating. That is where you will find the value of y. Okay, right in there. That's obviously 1.9 would be way too young. 4.0 would be too old. Okay, let's make it just algebraic. N is less than -3 or n is greater than 0. So let's graph the first constraint. N is less than -3. So open dot on -3, arrow going to the left. And then n is greater than 0. And hold on, I graphed this wrong. -3, not +3. A lot of hiccups today. N is less than -3 or n is greater than 0. Open dot on 0, an arrow going here, right? So in this case, unlike the last one where we found this nice tight window where y will be found, in this case I have a nice tight window, a little blank space where n will not be found. N can be found anything from -3.00 ... 1 all the way on to being 0.000 ... 1 all the way on to positive infinity. So in this case, we found this little window where n will not be found. Why is it so difficult today? N will not be found. All right. And you're just going to have to write that on your own. N's value will not be found at -3 all the way up to +0. That is what I can conclude about the value of n in this case. Compound inequality. We have two constraints on the variable, right? What about this one? Negative 4 is less than x, which is less than 7. So this could be rewritten as the statement says here. This could be rewritten with an and statement as x is greater than negative 4 and x is less than 7. So go ahead, graph this one on your own. Let's see if we get the same thing. Stop the video right there. So greater than negative 4. Let's graph that first constraint. It cannot be negative 4 if it has to be greater than. We're going to have an arrow going to the right-hand side because y's value, or not y's, x's value must be greater than negative 4. And x is smaller than 7. So another open dot. We're going to leave 7 open on the graph as an upper limit and graph everything down from there. And then where our solutions intersect is where you're going to find the solution space for x. Hopefully you got a graph that looks something like that. Negative 1 is less than or equal to x, which is smaller than 5. This could be rewritten as x is greater than or equal to negative 1 and x is less than 5. So let's go ahead and graph this one. Let's see if we get the same thing. Stop the video now. All right, so the first thing is x is greater than or equal to negative 1. So this time I'm going to use a closed dot on negative 1 because it is allowed to be equal to negative 1. Another way of saying this is at least negative 1. Okay? Let's see if I can draw using a pen. Should make my life a little easier. I'm just going to draw going that way. And then x is smaller than 5. In this case, I want an open dot on 5, an arrow going in the opposite direction. And wherever those two constraints, those two graphs intersect is where you're going to find the value for x in that particular case. This one's an and statement, so you're going to graph everything from negative 1 on to 4.9 repeating itself. Right? In this one, I'm going to have to do a little solving first, and I think there's a couple that are on your homework practice that are like this, where you have to do a little solving first. So I have to first start by dividing by negative 2 to solve for n. And negative 2n is less than or equal to 20. When I divide by a negative 2, the negative side becomes positive, and the positive side becomes negative. So what do we have to do? Well, we have to flip that inequality symbol. N is greater than or equal to negative 10 first. And n minus 1 is smaller than 0. So let's add the 1 to both sides on this inequality statement. And n is smaller than 1. So now I have the two constraints isolated for n. N is greater than or equal to negative 10, and n is smaller than 1. All right? So can it be, for the first constraint, for the first inequality, can it be equal to negative 10? And hopefully you're getting used to that line underneath is yes. It can be equal to negative 10. And the arrow is going to be going up this way. And since it's an and statement, I'm going to find a nice tight window that'll be shaded in for where n can be found. And n is smaller than 1. Positive 1 is my upper limit, arrow going down. And where those two arrows intersect, you could grab a highlighter or a colored pencil or something like that and graph the solution to the compound inequality, right? There's one more that I think you'll see from time to time, and there's an exception to the rule. It's called a but statement or a yet statement or a however statement, okay? If 2n is bigger than negative 4, but n does not equal 0, how do we graph this? Interesting, okay? So if 2n is greater than negative 4, let's get n by itself, do a little solving. What is going on, pens? Don't know what's going on with that. Let's see if black pen does anything different. Not really. What about if I use my mouse? I'm getting the pinwheel of death. Okay? That doesn't help me very much at all. If 2n is greater than negative 4, but n does not equal 0, well, hopefully you solved and you found that n is bigger than negative 2, and I can't draw that for you right now for some odd reason. I cannot draw that for you. Hopefully this video is working out and I'm not freezing up. but n is greater than -4. So hopefully you'll have an open dot on -4, or sorry, -2, and an arrow going to the right direction, an arrow going in the right direction. But n does not equal 0. So what you're going to have to do at this point in time is you're going to have to put another open dot on 0, meaning that 0 is the exception to this particular rule. It's the exception to this rule. And hopefully this recording took place and I'm able to save this and post it for you guys. Otherwise, this was a waste of time. But hopefully you got some insight on compound inequalities and enough to at least start your individual practice. Let me know if you have any questions.